Recording in progress.
Good morning, this is your Stats Sensei, Mr. Spensei, and this is the Death Packet, problems 11 through 20 for Classical Probability Unit 3A. So, number 11, let the random variable x represent the number of people living in a household in a certain town. The standard deviation of x is 1.8. Which of the following statements is the best interpretation of the standard deviation? First off, let's talk about standard deviation. The formula is the standard deviation equals the sum of x minus mu squared divided by n. Well, basically, this is the individual x's minus the mean. So how far an individual value minus the mean, we're going to square that distance, and we're going to divide by the sample size. So essentially, we're going to take an average. So it's basically the average distance the values are from the mean. So we're talking about the number of people living in a household, and we have a standard deviation of 1.8. So on average, for the average household, we expect it to be 1.8, to vary between 1.8 from the mean. So the number of people living in a randomly selected household is expected to be 1.8. No, that's how far we expect to be away from the mean. They didn't even tell us what the mean is, so we don't know that. The number of people living in a randomly selected household will be 1.8. No, on average, if we surveyed everybody, it'd be 1.8 people away from the mean. It could be the mean, it could be more than, or it could be exactly the mean, or it could be more 1.8 away from the mean, or more than 1.8 away from the mean. So not that. On average, oh, I'm liking this already. Because on average, in the long run, if we did it over and over again, the number of people living in a household varies from the mean, the distance from the mean, by about 1.8 people. And it's, yep, this individual distance on average, because we're taking an average, is 1.8 from the mean. So I like that one a lot. D, for random sample of households, the average number of people per household is expected to be 1.8. No, that's the definition of expected value or mean. It's not the definition of a standard deviation. For random sample of households, the average number of people per household will be 1.8. First off, that's a specific. We don't like that. Secondly, this is talking about a mean. It's closer to a mean than it is to a standard deviation. It's not talking about the variability. Number 12, the random variable W can take on the value 0, 1, 2, 3, 4. The expected value is 2.8. So they're telling me this is the mean, this is the average. Which of the following best interpretation of the expected value of the random variable W? Well, basically, first off, in the long run, if we did this over and over again, this is what we would expect to happen. So randomly selected value W must equal 2.8. First off, 2.8 isn't even a possibility. No, it doesn't have to be 2.8. The values of W vary by about 2.8 from the mean. That would be standard deviation, and we're looking for expected value, which is the average or the mean. The mean of a random sample value selected from the distribution will be. No, we expect it to be, or in the long run it'll be, or if we did it over and over again, it will be. A value of W randomly selected from the distribution will be less than 2.8 units from the mean. No, that really has nothing to do with either one of them. And so for values of W's repeatedly selected at random from the distribution, the mean of the selected values will be about 2.8. I would like this to have said about, but this is still the best answer. The Hockey All-Star game has the Eastern Division All-Stars playing against the Western Division All-Stars. On the Eastern Division team, there are 8 United States-born players, 14 Canadian-born players, and 2 European players. So 8, 14, and 2. All right. And that's for the East. On the Western team, there are 12 United States-born players, 8 Canadians, and 4 Europeans. So 12, 8, and 4. If one player is selected at random from the Eastern Division, so from this division, what's the probability, and one player is from the Western Division, so this division, what is the probability that neither player will be Canadian? So in other words, we can't have Canadian. Well, 8 plus 14 is 22, plus 2 is 24. Well, can't have the Canadians. So 8 plus 2 is 10. So 10 out of 24 for this one. On this one, we have 12 plus 8 is 20, plus 4 is 24. So we have 24 players. And 12 plus 4 is 16. So 16 of them are not Canadian. Well, each team should be independent because we're randomly selected from this team and randomly selecting from this team. So we're going to need to multiply. And 10 times 16 is 160, and 24 times 24 is 576. They did not reduce in their answer, and we see 160 divided by 576 is an answer choice. All right. Let random variable Q represent the number of employees who work at a certain restaurant on a given day. The following table shows the probability distribution of the random variable Q. 20, 21, 22, 23, 24. And here's our probabilities. We need to check, is this a valid probability distribution? 3 and 4 is 7, 8, 9, 10. So yes, that adds up to one whole valid probability. What is most likely supported by this table? Or which is best supported by the table? The most likely number of employees who work on a given day is 24. No, 30% work is 24. The most likely number, if I only had to pick one number, would be 23. Happens 40% of the time. So it can't be A. The mean number of employees who work on a given day is equal to the median. I'm going to say, you know what? I can look at this and go, it's skewed to the left. The mean and median probably aren't going to be the same. But as opposed to just intuiting it, let's put it in the calculator because I think that'll help out. So 20, 21, 22, 23, 24, I have that in L1, and I have the associated probabilities in L2. So stat, calc, one variable statistics, L1 for my list, my frequency or probabilities in L2, and I find out my mean is 22.7 and my median is 23. So yes, my mean is less than my median. So that's not, they're not equal. The mean number of employees who work on a given day is greater than the median. No, the mean is less. We just said that. The mean number of employees who work on a given day is less than the median number. This looks good. Let's check, make sure that E is not better. On a given day, the number of employees who work at the restaurant will equal at the restaurant occurs with equal probabilities. No, we see the probabilities are different. So D is our best answer. Number 15, this is a problem I don't particularly care for, but we're going to go through it. Let random sample S represent the age of the attendees at a local concert. The following histogram shows the probability distribution of the random variable S. All right, we can see that it's skewed left. And if it's skewed left, we know that the mean is going to be less than the median. Okay, so Alfonso claims that the distribution is symmetric with a mean age of 36. False. It's not symmetric. So the distribution is skewed to the right. No, it's been stretched to the left, so it can't be that. Skewed to the right. No, can't be that. So we're down to these two, skewed to the left with a mean age of 36 or with a mean age greater than 36. Well, that's a big question. So let's take a look at this. All right, so if I look at this and I add this probability, this probability, and this probability, I'm coming up with my median is here and my mean should be just to the left of it. So my mean is likely to be in the 37. All right, so no, the distribution is skewed to the left with a mean age greater than 36. And again, I don't like that. You can plug the values in and you'll come up with 37, but this is not the best problem for sure. Number 16, in a probability, in a parking lot with 200 cars, 50 cars are white, 30 cars are red, and 20 cars are silver. One car will be selected at random from the parking lot. If each car in the parking lot has only one color, which of the following cannot be the probability the selected car will be green? Well, green wasn't even listed. But we know that 100 out of the 200 cars are these colors. So that's 50%. All right, or 0.50. Well, I know I can't have more than 50%. I can have the green number of green cars or the percentage of green cars can be any value less than or equal to 0.50. So there might be no green cars. That's fine. 10% is definitely less. So, and they say cannot. So not that. 20%. Well, we can have 20% green. We can even have exactly 50% green. So that's possible. But we cannot have more than 50% because 50% plus 60% is greater than 1, and we can't have a probability distribution of greater than 1. It has to equal 1. Number 17. Let random variable X represent the number of movie screening at movie theaters in a certain city. The following table shows the cumulative probabilities. And by the way, this is cumulative. That's important. We're going to need to come back to that in a second. For the discrete random variable X. And by the way, if I add these up, they add up to more than 1. So this is 20%. The difference between 50 and 20 is 30. The difference between 50 and 60 is 0.1. 60 and 70 is 0.1, 0.1, 0.1, 0.1. And I've made a graph of it. At 1, we have 20%, 30%, 10%, 10%, 10%. It's like, oh, this looks like it's skewed to the right. Andromeda claims the distribution is skewed to the right with a mean equal to 4 movies. Is Andromeda's claim supported by the table? Well, it is skewed to the right, but we don't know where the mean is. So let's plug our data into the calculator. So if I go to stat edit, clear that out and clear that out because it won't take this long. And I'm going to go 1, enter, 2, enter, 3, enter, 4, enter, 5. Oops, skip 3. 3, enter, 4, enter, 5, enter, 6, enter, 7, enter. Scoot over, 0.2, enter, 0.3, enter, 0.1, enter, 0.1, enter, 0.1, enter. It's really important to convert those probabilities so that they add up to a valid probability distribution. And all I did was take this one and find the distance, this one take the distance, this one subtract and find the distance. So stat calc, one var stats, L1, L2. And I find my mean is 3.3. So no, it's not 4. All right. But it is skewed, but it's not 4. No, the distribution is skewed to the left. No, it's skewed to the right. So that gets rid of those two. So skewed to the right with a mean greater than 4 videos. No, it's skewed to the right with a mean less than 4 videos. And we just found out that the mean was 3.3. Our X bar was 3.3. All right, number 18. Let random variable U represent the field goal percentage for players in a basketball league. The following table shows the probability distribution of the random variable U. Fatima claims that the distribution of U is uniform with a median of 0.4. If it's uniform, every single one of these values would be exactly the same. So it's not uniform, and they're not the same values. And one thing I do notice about this is I need to sit there and check, is it a valid probability distribution? And when I added them all up, they added up to 1. Okay. So is Fatima's claim supported? No. So we can't say yes. Yes is the wrong thing, right? No, the distribution is uniform. No, it's not uniform. Well, now we talk about whether it's skewed right or skewed left. So if I sit there and go, well, this is 0.3, this is 0.4, 0.5, 0.6, 0.7. Well, this one goes up 10, then it goes up higher, less high, and less high. So it's going to be shaped like this. So if it does that, it's skewed to the right, so that means it gets rid of E. Now we need to figure out which one of these is right. So we need to put in these values. So we're going to go to stat edit once again, clear out L1, clear out L2, oops, get to L2, L1, there we go, 0.3, 0.4, 0.5, 0.6, 0.7, and our frequency, our probability, 0.1, 0.45, 0.3, 0.1, 0.05. stat calc, 1 var stat, L1, L2. And I end up with an X bar of about 0.455. All right. But they didn't ask for that. They asked for the median. The median is 40%. And I could have just sat there and go, hey, yeah, if I add those two values to get to 50, that'll work. So the distribution skewed to the right with a median of about 0.40. And that's what it showed on my calculator is 0.40. All right. Number 9, what are the mean and standard deviation of the payoff? Well, that should be fairly easy to do. We're going to go back to stat edit. And we're going to 0, 500, 5,000, 0.7, 0.25, 0.05. Stat calc, 1 var stat, L1, L2. And we expect 375. And our standard deviation is a pretty big number, about 1,082. So our closest value is 1,083. All right. Number 20. At a certain company, loan agents are paid based on the number of loans they close in a day. Based on company records, the number of loans that a randomly selected loan agent closes on a randomly selected day has a probability distribution below. So let's go ahead and enter that probability distribution. So stat edit. 1, enter 2, enter 3, enter 4, enter 5, enter 6, enter 7, enter 0.05, 0.1, 0.22, 0.3, 0.18, 0.12, and 0.03. Oops. Well, that didn't work out. 0.05, 0.1, 0.22, 0.3, 0.18, 0.12, and the last one, 0.03. All right, I've checked to see if it's a valid probability distribution. And we're going to go stat calc 1 var stat, L1, L2, and we expect them to close 3.94 loans. That's how many loans we expect them to close. All right. So the expected value is 3.94. How much money do we expect them to get? Well, it's 150 plus 50x. So what's 150 plus 50 times 3.94? So we expect his salary to be 347. Well, the expected value, the mean of x is less than the mean of y. That's true. So that's a true statement. The standard deviation of y is approximately 71. Well, let's go find out. So stat calc 1 var stat, and we come up with the standard deviation of x as being 1.4. So I need to plug that in. Remember, we're not going to add the 150. So it's going to be 50 times 1.4. 50 times 1.4. Oh, that's about 70. Yeah, this is true. The mean daily salary greater than 350. Well, when we plugged in, we came up with a salary of 347 because we went 150 times 150 plus 50 times the 3.94. And that equaled 347. So it's not greater than 350. So this is false. So that's my answer. All right. So the answer to number 20 is C. I appreciate you watching and I hope to see you on the next one. Thank you.